Also mute your cameras.
Okay, shall I share my screen?
Yes, please go ahead and get started as soon as you are ready.
Okay. Do you see that?
Yes.
Okay, great. Okay, so I will be talking about a very broad experimental overview on the spectroscopy program at LHCb. So apologies, this will be a very broad presentation. There will be a lot of results here. So I decided not to go into much details on anything, also because there will be several detailed specific talks during this workshop. And, you know, on the spirit of a wide variety of topics that I see that will be discussed in the workshop, I decided to get a very wide overview on the whole spectroscopy program. Why are we interested in spectroscopy? Well, because LHCb is perfectly suited for spectroscopy due to its high luminosity, high B and C quark production cross-section, and a unique dedicated design. So LHCb has managed to become one of the major players in the field of heavy hadron spectroscopy. And I want you to just have a look at this plot. Maybe most of you probably have seen this already. This is all the hadrons discovered at the LHC from 2011. So we have 62 new particles, and these are the ones discovered only by LHCb. So you see that the vast majority of new hadrons at LHCb, the LHC experiments, come from LHCb analysis. The spectroscopy program, as I said, is extremely rich, extremely wide, both in conventional heavy hadron spectroscopy and exotic spectroscopy. This is just a list of things that we do. Is not complete, but just to have an idea of what are the different topics that we have in our program. So excited mesons, excited conventional hadrons, let's say, and for the exotic part, of course, the Jpsi, which is the king of the exotics, but also so many other things, tetraquarks, pentaquarks, known chemonia, and just unexpected contributions that can happen while analyzing our data. For those of you who are not familiar with LHCb, LHCb is a single-arm spectrometer, and it's designed for high-precision flavor physics measurements with a very good primary vertex and secondary vertex resolution. So we're able to distinguish between between particles produced in the primary vertex and particles produced by B or D decays. And very good tracking system with a very good momentum resolution. And highly performing PID algorithms and hardware in general. So the shape of LHCb is of course optimized to measure mostly to catch most of the B quark production, which occurs at low angles. And we have a total recorded luminosity of 3 inverse femtobarns at 7 and 8 TeV for run 1, and 6 inverse femtobarn at 13 TeV for run 2. Okay, so let's start with the conventional spectroscopy. So the first thing I want to talk to you about is there's observation of a new excited BC state. This is supposedly the BC star 2s. In this analysis, we reconstruct BCs, and then we add 2 pions and just we scan the mass looking for narrow peaks. So we do see 2 different peaks. The first one, which is consistent with the BC star 2s, with a very high significance, more than 5 sigma. The second one is just a hint for now, so it's a 2.2 sigma global significance. So we can say that there might be something there, but this is not enough. And this is consistent, but more precise than the states observed by CMS. For Well, just remaining on the heavy B spectroscopy, we also observed two new excited B sub S states. This is done by combining a B plus with a prompt K-on. And then the B plus is reconstructed through the Jpsi K or the D bar pi final states. The signal is quite pure. There's less than 10% background in the peak. So what you see here includes only 10% background from the B mass, of course. And all the variables you see plotted here are the mass difference between the reconstructed B sub S mass minus the B and the K mass. You can see that there's a structure around 300 MeV, which is a bit more prominent for high PT, which are the bottom plots. And the left column is a tentative fit with one single peak. And on the right, you have the same data, but a different fit model with two different peaks. So the two peaks hypothesis is favored with high significance, although a single resonance decaying through both BK and B star K cannot be excluded. Is this favored but cannot be excluded? So under the two peak hypothesis, we have these two different states with masses and widths as reported here, and including the photon, their masses shift of about 45 MeV. We're also able to measure the sum of the cross-section times branching ratio. Now, again, for another excited state, an excited Mason state, this is for DS. This is actually motivated by the fact that the DS0 star and DS1, they are observed, but their masses are much smaller than the ones predicted. So there might be exotic candidates, but in any case, another additional input is required to distinguish that. So we did an amplitude analysis of B0 to D plus D minus K plus pi minus, restricting ourselves on the K pi mass, which is less than 750 MeV. And you can see a clear structure at 2.6 GeV from the right plot, which is more than, well, it's about 10 sigma significance, and the Jp is measured to be 0 minus. We also measure the mass and the width of the state, and in the end, this is a strong candidate for the 2,1S0 D sub S state. Now on to barons. So there was a search for an omega 0 BC and a psi 0 BC. So that's the first search for both beauty and charm hadrons, barons. This is done by just looking for peaks in the lambda C pi and the psi C pi invariant masses, as lambda C and psi C are both reconstructed as P, K, and pi. So that's kind of useful. No evidence for the states is observed, so upper limits are set at 90% confidence level. You can see the plots here with different also hypotheses on the lifetime. The one on top is using the lambda C pi final state. The one on the bottom is using the psi C pi final state. The upper limits here are on this R, which is the production cross-section multiplied by the branching ratio. And this is normalized with lambda B or xi B decays to the same final state. Then new excited xi B states. These are observed as narrow peaks in the lambda B K pi spectrum. You can clearly see them here on this plot. They have a very large significance with respect to one peak or to 0 peaks. So we measured masses and the widths. Well, actually on the widths, we only have a limit at 90% confidence level. You can find on the third and fourth bullet. They are consistent with the predicted 1D xi B doublet with quantum numbers 3/2 plus and 5/2 plus. Then on to Chalmonia. this is the study of the Jpsi eta K decay, just searching for Chamonia or Chamonia-like exotics into this final state. And actually, the only contribution found are the Psi2 3823 and the Psi 4040. As you can see, they are the red peaks. The red peak on the left plot and the red peak on the central plot. You can also see the Psi2S, which is used as normalization in the left plot. So basically limits are 90% confidence level on the branching ratio of a hypothetical particle decaying into Jpsi eta are set, as you can see on the right plot, scanning on mass values of this hypothetical resonance from 3750 to 4700, and you can see some high fluctuations in this plot, but in the end they're not taken alone, they're not statistically significant. So in the end, there's no observation of any other state apart from those two. Okay, so let's move on to exotic spectroscopy. So first thing I want to talk about the KC1 3872, because there have been a lot of improvement in recent years on the knowledge of this state. So this is a study of the line shape, which is basically, this is a study of the analytic structure of the amplitude near the threshold, which is the D0 bar, D star 0 threshold, as the complex amplitude is a function of the square root of the energy. We have the two shaded Riemann surface, and we found two poles using the flat amplitude for this channel, for the D star D bar channel. The one on the left here is on the physical sheet. The one on the right is on the unphysical sheet. And as you can see, from the one from the left prefers basically the bound state description, although a virtual assignment cannot be ruled out as is about as high as 2 sigma. This can also allow to set a limit on the binding energy, which has to be less than 100 keV, and with the probability of a compact component to be found within the wave function of less than 33%. Then on this same analysis and another one also measured the mass of the KC1 3872 with the highest position up to now, as you can see on the left plot. And more importantly, they measured the width of the state for the first time. So this is the first time we have a non-zero width of this state. So there will be more information on the KC1 3872 on the dedicated talk by Tomasz on Thursday. So I will not go into more details on this. Then this is probably like a golden channel for exotics, the B plus and Jpsi phi k, which is notorious for the high number of exotics that have been found already in run 1. So here you can see on the plots three different projections of the amplitude fit. On the left, there's the phi k mass, in the center Jpsi phi mass, and on the right the Jpsi k mass. The data shown on the first and second row, or top and bottom row, the data are exactly the same. The only is just run 2 data. The only difference is the model. So on the bottom, you can see what happens with the model used for run 1. And on top is just a new model, which includes also new states and some new contributions, which are listed below. So the old state, the states that were already been observed are confirmed, and then new states are added to this run 2 model, including 2 ZCS exotics. So this is the first observation of exotic states with a minimal core content of CC bar, US bar in the Jpsi K final state. Then on to, this is another Similar, if you want, exotic found in the Jpsi, in the B sub S to Jpsi KK pi pi decay. It is found basically it is found in the same final state as the ones we saw in the previous slide. So it's always Jpsi phi. This one has a mass which is slightly different from a hypothetical. Not hypothetical, sorry, from one of the states that have been already observed in the previous analysis I showed you previously. So this is not, it's still unclear whether this is the same state as the X4700 from B to Jpsi phi k. So more additional studies are required, but for now we know that this state is observed in B sub S decays. Then, okay, so this is probably one of the most famous analysis in recent years. So we observed a structure in a Jpsi pair, in the Jpsi pair mass spectrum, so Jpsi. Again, on the two plots here, the data are the same. It's just the fitting model which differs and basically differs only in the description of the threshold enhancement. So on the left, the threshold enhancement is described by two different resonances. So basically two S-wave Breit-Wegeners multiplied by a two-body phase space. On the right, the threshold enhancement is described by by interference of the signal resonance, signal Breit-Wegener, if you want, with the single parton scattering background, which is the purple one. So in both cases, we have very high significance, so we're not able to distinguish which one is more correct than the other. In any case, it looks like there's a contribution there at a mass of 6,900, and definitely we need more studies to investigate the nature of this state. But if it's confirmed to be an actual resonance and an actual true state, then this is the first observation of an exotic hadron composed entirely by heavy quarks of the same flavor, just charm in this case. Well, rather charm, anti-charm, charm, anti-charm. Then let's get to B to D decay decays. For this particular state, this particular decay, we had a first model independent study. So this is, I think, up to now. Well, now it's about a classical methodology, but it's just for those of you who are not familiar with it. This is a study of the resonance structure of this decay, done by expanding the DD helicity angle in terms of Legendre polynomials, and then basically adding by only limiting the maximum momentum that the maximum J, maximum angular momentum of the resonances that can contribute to this decay. You can check whether the data are well described by this approximation or not. So in this specific case, you see that on the left plot there's a bit of an excess about around 2.9 GeV, and in fact the hypothesis that only D plus D minus resonances up to spin 2 can describe the data is rejected with a significance of 3.9 sigma. So of course then we're interested in going deeper in there and see what exactly is happening. So we did an amplitude analysis of the same channel, and we saw that two Breit-Wegeners describing two states decaying into D minus K plus significantly improve the fit. And they are found to be one spin 0, one spin 1 with roughly the same mass. Okay. And you can see them here in the top right plot corresponding to that big peak, to the highest peak, basically. And there's no evidence for the Kaiser 03860 state decaying into D plus D minus reported by Bell, which I forgot to quote here. I'm sorry. The Kaiser 23930 contribution is found to be better described by two states. This is another surprising thing, if you want. And there's a reasonable agreement with data when we include two new Breit-Wegeners decaying into D minus K plus. So if we interpret these two Breit-Wegeners as resonances, this is a first clear observation of exotic hadrons with open flavor, and without a heavy quark-anti-quark pair. So the minimum quark content here will be CD S bar U bar. And you have more information on this particular decay in this particular channel on the dedicated X2900 talk by Ritting on Wednesday. Okay, so move on. Okay, so another very huge achievement is the discovery of a doubly charmed tetraquark. This is a narrow peak in the D0 to 0 pi spectrum, which is just below the D star plus D0 threshold, which is the green vertical line, as you can see, very close to the peak. This is consistent with the ground isoscalar TCC tetraquark plus, TCC plus, which have a minimal quark content of CC U bar D bar. So that will be the first, sorry, the first observation of a tetraquark with CC instead of CC bar, for instance. So I will not go into details on this. Sorry, as there will be a dedicated talk by Misha on Wednesday. So please go and see that if you're interested. And then on to the last topic on the exotic field is pentaquarks. So sorry, but I'll try through it. So on pentaquarks, we have two new states. The first one is the PC 4337, which is observed in the B sub S to Jpsi PP bar decays. So it's actually observed both in Jpsi proton and Jpsi antiproton. The plot here actually combines both Jpsi proton and Jpsi antiproton by just selecting the proton or antiproton with the highest BT. It's a nice trick to enhance the signal contribution. And you see that both the PC plus and PC minus decaying into proton and antiproton. The peak is quite prominent there. It's the blue shaded area. So we can measure the mass of the state, the width. And in this channel, there's no evidence for the other famous pentaquark 4312, nor for a predicted blue ball state, is the FJ 2220. Again, I will not go into much detail here. There will be a dedicated pentaquark talk by Liming on Friday. And our second new pentaquark is the PCS state 4459. This comes from an amplitude analysis of the Xi-B, the Jpsi lambda K minus. And you can see that on the plots as the light blue filled histogram, which is particularly, I mean, it's prominent on the right plot as a narrow peak. On top of that, two new Xi star minus states are observed, so the 1690 and the 1820. And there's, as I said, evidence for this new pentaquark with strangeness. So the The mass is below the Jpsi is 19 MeV below the Jpsi D star bar 0 threshold. So I forgot to write threshold here, but the JP is not yet determined due to limited yield mostly. So improvements are foreseen for the next years. And again, you can see you can have more information on this and get a dedicated talk on Friday. Okay, so I think I'm done. Let's just conclude by saying that, as I hope I showed you, the heavy resonance spectroscopy is an extremely rich and productive field, both for conventional and exotic states. And actually, new conventional and new exotic hadrons are discovered every year. And well, if you have a look at the plots I showed in at the beginning, you can also see that they're being discovered every year faster and faster. So we can be a bit optimistic about the future then, if we care to extrapolate. And as I said before, LHCb has established itself to be a major player to its particular design and particular performances, which are perfectly suited for spectroscopy. Spectroscopy of heavy hadrons is not just something we do for fun. It's crucial to understand QCD dynamics and binding rules, which are even today a bit obscure. Also, many excitation spectra are still mostly unexplored territory, talking about the BC or the BS, for instance. But not only that, we're missing entire spectra for baryons. So there's still a lot of work to do. And non-conventional exotics, when I say non-conventional, I mean something which is not a germanium, so open flavor exotics or doubly charmed exotics, for instance, they've been discovered recently. So that opens a new door on a new subfield, if you want, of exotic spectroscopy. So with these thoughts in mind, let me just conclude with some prospects for the LHCb Run 3. Which will start with an upgraded detector and a software-only trigger with improvements on hadronic triggers. So LHC experiments will be the only explorers of the BC spectrum in the near future. So LHCb will clearly play a major role in it. Then heavy baryon spectroscopy has already started in Run 2. So clearly that will go on and will definitely improve somehow, with a focus on BC searches, which I showed you. We just started doing that. Then for Run 3, we will have also access, hopefully, to BC tetraquarks and pentaquarks, if they exist, and BB bar spectroscopy and exotic spectroscopy. This is something we haven't been able to do up to now. For sure, we'll manage to confirm or reject, but hopefully confirm the pentaquark states, including the new PCS, and measure their properties. And then this is something a bit more technical, but I think it's quite interesting, is that for Run 1 and Run 2, the exotic hadron searches rely heavily on the Jpsi to 2 muons for reconstruction. So we usually take the Jpsi and then we combine it with other things. That's because it gives the best performances in terms of resolution and efficiency. In Run 3, with the removal of the L03 trigger, we'll be able to access fully hadronic final states. So this will allow us to study open flavor exotic states which are fully hadronic. So we don't have to rely necessarily on the Jpsi in the future for Run 3. We will continue to do so, but that won't be a limit. Okay? And I think that's it. Thank you very much.
All right. Thank you, Lorenzo. So questions?
I see many hands raised. Can you see that?
Yeah, my screen somehow doesn't update.
Okay. Frank Nerlin, Christoph, and wait.
So could you please call on people that you see? Because
okay, in order. Frank, would you like to talk?
Yeah, thank you. So Lorenzo, thanks a lot for this very nice overview and this these rich results which you have obtained with LHCb. I have a question to your page 17, and it's also connected to 22. So you reported and presented to us a nice observation of that Z sub CS strange partner candidate for the ZC3900 or similar here from your data. Probably you're aware of the observation by BESS3 that we did on a similar state in the open charm decay to D sub S D star. And my question is whether you looked at this also. I mean, on your later page 22, you mentioned an open charm, but that is not the D sub S D star. It's D plus D minus, isn't it? Can you say a word on the similar decay channels where we observed such a state with the BESS3 data?
So that did what's the final state again? Sorry,
D sub S D star.
D sub S D star. Okay. Well, as I said before, the problem with that, so D sub S D star. Yeah, the problem with that is that we're lacking a proper hadronic trigger suitable for exotic studies up to now. So this particular decay was not, so for this particular decay we didn't actually expect any exotic here. Okay, so this was a decay which was studied for, well, mostly for to analyze the resonance structure, and so the way we trigger on hadronic states, it's not optimal for, to have large statistics, which is usually what you need. So I guess I'm not aware, to be honest, I'm not aware of anything working on that at the moment in LHCb. I'm sure that it will be done in round 3 for sure. And I have to think if it can be done with round 2 as well. Probably it's going to be very hard. But as far as I know, I might be wrong, but as far as I know, we're not working on this at the moment.
Okay, thank you. Yeah. So we're looking forward to the round 3.
Sure.
Okay, so next in line, let's go with the experimentalist first, Dimitro.
Yes, I would like to give a very short comment also regarding the slide 17, where you mentioned the new states that were observed. You mentioned that.
What is your question?
It's not a question. It's not. It's more a comment.
I cannot hear you.
Can you hear me?
I can hear. Yeah.
I can hear.
Dimitro?
Yes. It seems that everybody can hear me except for Elisabetta.
Yeah. I can hear.
Go ahead, Dimitro.
Okay, so I just wanted to comment that meanwhile it was correct to mention that the model changed because more K-star states were included in the model and all the rest, but also what is more important to my mind is that the data is not identical. The previous paper that was published on this matter included only run 1, and the later paper published in 2020 included also run 2, so it was 9 in Worm's femtobarn, and it was the reason why they were able to distinguish 5 more new states. So the data is not identical.
No, yeah, maybe I didn't say it probably. What I meant is that in this plot here, the top plot and bottom plot, the data are identical. It's just the model that changes. Okay, I'm not saying that. So the bottom plot is the same data as the top one with a different model. This is just a check of using the old model on new data. And you can see, for instance, on the bottom right plot, that doesn't work. So that's what I meant. Okay, it's not. Yeah, I mean, you're right. You're right. But this plot here is showing the same data.
Yeah, let me add to this, since I was involved in this analysis. It's true that there were minor changes in K-star model, but this is not what was important. What was important is a lot more data. So it's just much larger statistical precision that required all these new states.
Yeah, and if I may interject, Tomasz, maybe you can quickly comment on Frank's discussion of this BESS3, the connection with the BESS3 result.
Yes, so there is this one state that close to 4,000, which is very close to state with same quark content, but discovered in different channel by BESS, by scanning. I believe this was D sub S D. I'm sure one of them was star.
D star, D sub S,
Yes.
D star, and D sub S star D.
Right. But it's not clear that this is the same or different state, because the state observed here has significantly larger width than the one observed at BESS. And let me also remind you that a lot of narrow Z sub C states observed at D plus E minus were not observed so far at BD case, and vice versa. Many broader states observed in BD case were not seen in plus minus production. So that's something that will require more data and understanding what's going on here. But possibly there is more than one dynamics involved with the same quark content here. All right, I see there are also questions from Fioris. Christoph?
Yeah, we have Christoph and Olojo. Christoph?
Thanks, Lorenzo, for the nice talk. I actually have more comments than a question. I would like to request for the future, at least not to show anymore without remarks the Breit-Wigner-Witz of CX, simply because, as you reported nicely, a proper analysis of CX, since it couples so strongly to the D star, D bar, really requires a Flatey analysis, and the pole locations that emerges from that analysis is clearly inconsistent with the Breit-Wigner-Witz that you quote. So the Breit-Wigner-Witz is merely a parameterization of what is seen rather than reflecting a property of the particle. Therefore, I would kindly like to request to not show that, at least not without a corresponding remark, that this is not a physically sensible property of CX. Thank you.
Okay. This is the only thing we have right now. So,
no, that's incorrect. You have a pole location. You have studied the pole location, and the pole location, the imaginary part of the pole location, is connected to the physical width. Therefore, you have more and better information than quoting the Breit-Wigner-Witz. The Breit-Wigner-Witz is really obsolete after you have a Flatey analysis.
Well, Christoph, many of these analyses, they did try single channel K matrix. So this gets away, at least when you have more than one state in the same wave with the same quantum numbers. That was usually tried, and this is in the spirit of getting away from Breit-Wigner's. But I personally think that yes, people should take all these complicated amplitude analysis with a grain of salt, because what I think is even bigger problem than Breit-Wigner's is that coupled channel effects are neglected so far in most of these analyses, and so there could be actually pretty significant effects from coupled channels.
Or maybe we come back to that in today's evening discussion, but the Flatey analysis that was done for the X, as you know well, by LHCb, was a coupled channel analysis. It included both the discovery channel, the Jpsi pi and the DD star, and also the omega. Therefore, it was a coupled channel analysis, and that reveals the at present best existing pole location of the X. And this really makes the Breit-Wigner parameter obsolete.
Yes, but you know, this discussion should be specific to the states. X is extremely narrow. So like we were just looking at rather broad states. So I think, you know, the limitations of what has been done are specific to particular states rather than generic.
Okay, maybe this is something we should pick up in the discussions later this
Yeah,
afternoon.
absolutely. This is why we are meeting together. Julio?
Yes, Eulogio.
Yeah, sorry.
So
put your first name in
I
Zoom thing. So
I have
could
to side.
type it.
I have to side with the Hanhart Christoph, on the that you should not abuse, from the use of right-wingers. And actually, the analysis, using, properly unitary, frameworks, putting couple channels, particularly when you are close to threshold, is not more difficult than what you are doing right now. If it was extremely more difficult, I would sympathize with you, but it is not more difficult. It is equally easy. So I encourage you to do this kind of analysis in the future. Okay, but my question was different, or my comment actually, if you go to page 21, I have a couple of comments there, one comment and a question. Page 21, yeah, well, yes, page 21, you see, and then the 22 maybe also. Next one, that's it, look, there you say something there so beautiful. No evidence for the Jpsi 3860 of Bell. Eh? I laugh at that because, I had, some heavy discussions with the Bell people concerning the state, because, Wang, Liang, and I, we just look at that, in much detail of the analysis, because the plus and minus going to Jpsi DD bar, and then we found that there was no reason at all, to claim that set, absolutely none. You only have to divide, the cross section by the phase space, and you see nothing. It's flat. The distribution is just flat when you divide by phase space, no peak at all. So I never understood how, the Bell people, claim, that state. Anyway, our paper is published, and I'm very happy, that you found there that you don't see any evidence for that state. Instead, you found
all
that.
right.
So we agree.
Yeah, thanks
Yes,
for this
I am
comment,
very,
and I agree
very happy because you solved.
that we discuss this more later. So any other comments?
Yes, the comment now is, or the question rather is, you see, now go to the format picture, the format transparency, format slide, go to the format slide there, it said, you have there, in the D plus, D minus spectrum, you have there a beautiful peak that comes from the decay of the 3770, which is fine. That's a vector meson that decays into D plus, D minus, because that's open. Now, since you do so good partial wave analysis, couldn't you, do some partial wave analysis for this, reaction, such that you could isolate the S wave part of the D plus, D minus? When I say that, because, there are many theoretical works, that predict a bound state of DD bar. And recently that was corroborated by one, lattice calculation by Sasa, Prelovsek, and collaborators. So I think, you have something to say about that. If you measure, close to threshold with good precision, but also doing the partial wave analysis to isolate the S wave of DD bar.
Well, there will be more data in this channel in the future. I'm sure it will help. But keep in mind that this amplitude analysis in BD case, they are not as powerful as partial wave analysis in scattering experiments. And there are more ambiguities between different contributions. So anyway, I think we should move on to the next talk and save more discussion